Good afternoon, everyone. Thank you all for joining today's seminar. It is a great pleasure to have Professor Wei Wu here with us today for today's seminar. Professor Wu is an associate professor at the Department of Electrical and Computer Engineering at University of Southern California. Before joining USC in 2012, Professor Wu worked as a research associate and senior scientist at HP Labs. His work includes nanoimprint lithography and applications in nanoelectronics, nanophotonics, plasmonics, chemical sensing, and nanoelectromechanical cells. Professor Wu has co-authored many scientific publications and conference presentations and has been awarded more than 118 US patents. Professor Wu is also co-editor and associate editor of a number of scientific journals, including the Applied Physics A, as well as the IEEE Transaction on Nanotechnology and Nanomanufacturing and Metrology. Professor Wu has received the IEEE Nanotechnology Council 2015 and 2016 Distinguished Lecturer, as well as the USC Stevens Center for Innovations Commercialization Award in 2020. So it is a great pleasure to be able to host Professor Wu here today and learn more about his work on a memristor-based hybrid analog digital computing platform for mobile robotics. Before I turn it over to Professor Wu, I would just like to remind our audience that you can ask your questions at the end of the talk, either directly by raising your hand or type your question in the Q&A feature of this webinar. So with that, Wei, thank you for joining us here today and for your time. We're very excited to hear about your work. I turn it over to you.
Well, thank you very much. And thank you very much for your introduction. And also thank you very much for hosting me and inviting me to give me this great opportunity to share our work. This is MIT, right? And not everyone got a chance to give a seminar at MIT. And good afternoon. My name is Wei Wu from USC. Today, I'm going to talk about a memristor-based hybrid analog digital computing platform for mobile robotics. Well, I know this is a nano seminar series, but believe me, there's nano inside. So even I didn't put in the name nano in it. This is full of nanos. Okay, so now we overheard people talk a lot about machine learning, artificial intelligence, deep learning, etc. And if you think from hardware point of view, people would, so the hardware for artificial intelligence or machine learning is basically people trying to build artificial brain. Since we are trying to build artificial brain, so let's look at the human brain first. And for human brain, it consists of three parts. There's just a cerebellum, or so-called big brain, or cerebellum, that's so-called small brain. And there's a stem. Stem is in charge of breath and heartbeat. And who cares about breath and heartbeat? And let's look at the big brain and the small brain. Well, big brain is in charge of logical thinking, perception, decision-making, a lot of things. And the small brain basically in charge of keep you in balance. And most people work on the big brain, and because big brain is the most exciting part and the most useful part. And but we want to start from something simple first. And so we want to see, can we build artificial small brain cerebellum? Well, so as we said, the function of a small brain is basically keep you in balance. But how can you stay in balance? It needs two functionalities. One is so-called sensor fusion. Basically, you have all kinds of sensors on your body. You synthesize the information you got from the old sensors. Then you know, okay, I'm leaning to the left or I'm leaning to the right. And if you're leaning to the left, you try to push yourself to the right. If you're leaning to the right, you push yourself to the left to keep in balance. So this is the second functionality, is basically a control algorithm. So for the cerebellum, in order to realize artificial cerebellum, you have to have those two functionalities. Actually, if you want to have a good small brain, for example, for a robot, what do you want? You of course want this to be fast, and you want to consume low power. And if you have many degree of freedoms, and probably you also want it to be parallel. And Actually, if you think a little bit more of this, you'll probably realize one thing. This is actually probably a very good application for analog computing. Well, people talk about analog computing for a few decades already, right? And for analog computing, well, you do everything in analog domain, so you don't need to do ADC, DAC conversion. There's less overhead, so things can be fast and low power consumption, etc., etc. But we all know, after people talking about analog computing for a few decades, nothing really much happened. Well, the real reason is for analog computing, you don't have enough, your precision is not very high. It's not like in digital computing. You can have as many digits as you want to make as precise as you want. But for analog computing, your precision is basically limited by your signal to noise ratio. But if we think about the functionality for small brain, do you really care about whether to know if you are leaning to the left by 1 degree or 1.1 degree? No, you don't really care about it. But you want to have a fast response. You want to be able to control yourself and before you actually fall down, right? So because for this application actually has much lower requirement on precision, so let's make it actually very good for an application of analog computing. And actually, not surprisingly, 40 years ago, and people already proposed to use analog computing to do the control for robotics. And of course, again, we know nothing really happened in the last 40 years. Well, the real reason is we don't really have the proper device for a good hardware implementation of analog computing for artificial cerebellum. But actually now we already have an answer. It's a memristor. And the memristor actually is a nano device. And so today, this is actually my talk. So in the first part of my talk, I'm going to talk a little bit about memristor, especially on our recent work, how to engineering the characteristic of memristor in order to meet the requirement of certain applications. And then I will talk about the analog computing implementation based on memristor to implement a cerebellum for the simplest robot. And this simplest cerebellum actually has basically two functions: sensor fusion and the control algorithm. And in the end, I will talk a little bit about future work. And so let's talk about memristor first. Well, memristor is basically two terminal device. And you have two electrodes, and you have some switching stack sandwiched in between. And within the switching stack, when you apply a voltage high enough, and then the ions inside, well, actually there are several different working mechanisms. And for this specific one, the ion inside the switching stack can move up and down. And because the ion moving up and down, it forms conduction channel inside. And then you can have a high resistance state or low resistance state. And actually, you not only can have high resistance state and low resistance state, you can actually also tune it to have different conductions. And of course, memristor have been around for a while, and people have been trying to using memristor for various applications. And however, for different applications, actually, there's a very different requirement of the characteristics of memristors. And so in order to meet the requirement of specific applications, people have been trying to engineer the memristor through or using different switching stacks, different electrodes, and different stack thickness. And recently, actually, we found another new way, a new knob we can tune. We can turn to tune the characteristics of memristor. And this actually through the controlling the crystallinity of the switching layer materials. So this is the specific memristor structure we are using right now. So we have top electrode and bottom electrode, both made by platinum. And the switching stack consists of a tantalum and the aluminum oxide layer. And the aluminum oxide is deposited using atomic layer deposition. And the fabrication process actually fairly straightforward. Just put one electrode, then put switching stack, and put another electrode. And the one thing is, when we deposit this aluminum oxide layer using atomic layer deposition, when we deposit those at a different temperature, actually the aluminum oxide layer will have a different crystallinity. And here it shows XRD data about of the aluminum oxide layer deposit at a different temperature. And you can see when we deposit this aluminum oxide layer at 80 degrees C and 120 degrees C is amorphous. And one is deposited at 160 degrees C and 200 degrees C. They are polycrystalline. And actually, here summarize for the summarize the property. And for at one is deposited at 160 degrees C, and the grain size, the average grain size is about 150 nanometer. One is deposited at 200 degrees C. In the grain size is about 207 nanometer. And we also measure the refractive index, and you can see when it was deposited at a higher temperature, the refractive index getting slightly higher. That basically means the material is getting denser. And without go through much details, let's just look at TEM images. Here shows the TEM image of the aluminum oxide layer deposited at 80 degrees C. You can see this is the zoom-in view. You can see it's amorphous. And here is the aluminum oxide layer deposited at 200 degrees C. And you can see it's polycrystalline. And you can see the crystal structure here. Well, when we're using the aluminum oxide deposited at a different temperature to build a memristor device. And here actually we built exactly same memristor device. And for this device, the aluminum oxide layer thickness was 8 nanometers. And this was the first scan, IV scan of those 4 different devices. And first of all, we know when you have a memristor device and you can do so-called forming device after build it, you basically scan it, switch it on and off a few times. Depending on how hard you switch it on or how hard you switch it off, actually you can have different IV curves for the later scans. But this is the first scan. And then you can see even the device has exactly same stack thickness. They behave very differently. And this is 80 device deposit with aluminum oxide deposit at 80 degrees C. This is 120, and this is 160, and this is 200 degrees C. So you can see just the crystallinity change. It has a big effect. And of course, and then let's just look at if we want to use those devices as a memory device, and what you do, you're using pulse at a relatively high voltage to switch on and off, or off. Then you're using a pulse at a relatively low voltage to measure the conductance. And actually here shows when we're using pulses to switch those devices on and off. And you can see they behave very differently. And actually, if we look closer, and you will see, actually, this 120 degrees C device actually seems perform the best if we're using this as a memory device. Best means it has the largest on-off ratio, and also the spread of the resistance in both on and off states are narrower. And here actually just show the statistics. You can see 120 degrees C, the red color one, actually has the best performance. Well, what that means if you want to build a memory device, if you want to build using this as a memory device, and then you want to deposit your switching layer at the highest temperature, still keep the switching layer amorphous. And in this way, the device have a larger on-off ratio, and the performs more consistent as a memory under the pulse when you switch it on and off. But of course, we are more interested in using those devices to implement implement a small brain for the simplest robot. So we also want to see, can we tune those devices into different conduction states? And here shows one way you can tune the device to different conduction states by setting at a different compliance current when we switch it on. And if we're using 280-degree deposit aluminum oxide, and then we can switch to about 31 states. And however, the device with aluminum oxide deposited at 200 degrees C, you can see it can be switched into 157 states. And so you can see now we have this nice device can be tuned to different conduction states. And of course, here we also shows the is programmed to 10 different conduction states with equal spacing. And we just want to show you actually we can control the conductance reasonably well. So, and here, of course, we also want to be able to tune it to different conduction states, and using this simple setup, and using control it with an Arduino or controller. And here is the a package. And when we took this picture, we haven't glued the memristor on here, but you will see some picture later. And so this is the package to program it using pulse. And when we program using pulse, then we actually can also put a transistor in serial. And just by applying proper voltage on the gate of the transistor, and also proper voltage across this transistor and the memristor series, then we can control the current that go through the memristor when the memristor switch on. Using this way, we can control the memristor. We can program the memristor to different conduction states. And of course, when we reset it, basically switch off, or we just bypass the serial transistor. So there's a diode here. So this is actually the key idea how we program this. And then it's just controlled by Arduino. And this is the PCB board. And here actually is just SD card data logger. So we can actually read the data out. This is just how we store the program data, experimental data, then read it out. So we can write a paper. But for the real application, we don't need this. And so this is a circuit diagram. So this is the setup. So just let's look at here is the programming. And you can see we just apply a series pulse, one pulse to program it, and another pulse to read the conduction states. And here actually the pulse to switch it off. And of course, when we reset it, we have to apply a negative bias to switch it off. But let's just look at here actually just shows the current after each programming pulse. After so you can see we can program it to have a higher, this memristor to have a higher and higher conduction and conductance, and then we can also program to lower conductance. Okay, so now we have this nice device, and with this nice device, we can program it and to different conduction states. And now let's actually go talk about the real fun part, the implementation, hardware implementation of the simplest cerebellum for the simplest robot. And of course, in order to do this, we need to have two functionalities. One is the sensor fusion, and the other is the control algorithm. And for the sensor fusion part, we implemented an analog common filter. And for the control part, we implement a very simple PID control. And now let's look at those. Okay, so the robot we are using as a demonstration tool is really the simplest possible robot. If it's just a two-wheel car, the self-standing car, it only has 1 degree of freedoms. So that's really the simplest. And here actually is a picture of the car with everything installed. And actually you see two boards here. And on each board, we have a chip per carrier. And on the chip, we have a memristor chips. And then here you can see, actually on the right-hand side, that's the sensor fusion part. On the left-hand side, that's control algorithm part. Now, let's look at in more details. And this self-standing car is basically inverse pendulum. This is the system diagram. And this actually shows what we have is, and we have a memristor common filter, and to synthesize the signal from a gyroscope and accelerometer. And then after that, the result after common filter will be fed into a PD controller. Basically, the common filter tells you what's the state, or what's the angle the car is at now. And then it tells the PD controller, and the PD controller actually will control the motor rotation of the motor. Actually, more precisely, it will send signal to the motor controller, and the motor will turn and to keep in balance. And for this part, actually, is all in analog domain. The common filter and the PD controller are in analog domain. But the motor control module actually is in digital domain. It's a digital motor. So that's why we call it a hybrid computing platform. So now let's look at in this. Okay, so here the sensor fusion we are implementing here is a common filter. And the common filter is probably one of the most widely used sensor fusion algorithm. By the way, common filter was invented by Dr. Common. And I checked his wiki, and Dr. Common actually graduated with undergraduate and master degree from MIT. And not surprisingly, of course. So the basic, actually the common filter actually was invented for the Apollo project. The basic idea actually was this. And so you want to send a satellite to the moon, and but you have to know the location of your satellite. But when you measure the location for your satellite, and the uncertainty will start to diverge, and eventually the uncertainty is too big. It will be almost impossible for you to land on the moon. And then how you do this? Then actually there are two ways to know your current location. One way is to do direct measurement, and the other is actually if you know the location of the previous time frame, and you know your current velocity, you can always predict what is your current location just by using your previous location plus the velocity times the time, right? And so now you actually have two ways to know your location. And if you combine both and together, actually you can have a more accurate result. And this is the basic idea of a common filter. And but of course, for the common filter, there's some parameter called the common gain. And the common gain basically is this: you have two ways to know your location. One is the direct measurement, the other is a prediction. And based on which one is more accurate, and then you should put higher weight on it. And the ratio between those actually is so-called common gain. And of course, for our case, and we actually implemented a continuous time common filter, but basic idea is the same. And in order to know your current angle of the self-standing car, and you can either measure it directly using the accelerometer, or you can predict what is your angle by knowing the previous angle plus your angular velocity times time. And the angular velocity actually can be measured using gyroscope. And so this is really the simplest common filter we have. And you have the signal from the accelerometer, you have the signal from the gyroscope, and then we're just using this very simple analog circuit. This is an operation amplifier. using this very simple analog circuit to synthesize this and then to know what's the angle estimation now. And of course, the common gain actually is represented by a memristor. And you just tune the conductance value of your memristor, and you can tune the common gain of this very simple circuit. And here actually shows the circuit. The circuit put on this board, and this is the gyroscope, and this is the accelerometer, and this is our memristor is here. And when we put a memristor chip here, but actually only use one memristor out of it, and then it's connect to this. And as for a simple circuit like this, and of course, this circuit is fast. There's no analog to digital conversion. No, there's no digital to analog conversion, and it's basically just RC delay here. And so actually, the latency of this is less than a microsecond. And actually, there's a common filter coming with the self-standing car itself. It's a digital common filter. For that one, actually, the latency is about a few milliseconds. And then let's have a look. And so we put this board on this robot arm, and then we connect the signal to a oscilloscope. And let's have a look. When this arm swing back and forth, and you can see on the top, the yellow color signal is the raw data of the angle is measured. You can see it's relatively noisy. And the bottom one actually is the angle synthesized after the common filter. And you see it looks much better now. Oh. Okay, then of course, in order to achieve this, we have to have a proper common gain. And proper common gain means, and you need to put in proper conductance of your memristor. And if you don't have the proper conductance of your memristor, your common filter can be either undershoot or overshoot. And of course, then actually, when the first time we show this result, and someone asked us a question, why do you have to have a memristor here? Well, in this circuit, you can just replace this memristor with a resistor, right? And you calculate what should be your common gain. Then you put a proper resistor here. Why bother with a memristor? Well, actually, that's a very great question. It turns out the common gain is determined by the noise level of your prediction and your measurement, right? And the noise level of your device actually are different from each other, even it is exactly same model. For example, we bought 4 identical gyroscopes here, exactly same model. And when we put those 4 different gyroscopes in our system, and you can see for gyroscope number 2, the common we have for the proper common gain. We are using the exact same common gain here. We're using the exact same conduction value of our memristor in the circuit. And you can see for gyroscope number 2, the common gain is perfect. But for the other 3 gyroscopes, obviously the common gain is not optimal. And not only this, actually, the noise level of the device also depends on temperature. For example, at 29 degrees C, and our system has the perfect common gain. But when it's too cold or too warm, and obviously we need to change the common gain. Because of this, you want to have in your circuit, you want to have a device with a conduction value which is tunable, and then it will be much convenient, much easier for you to implement this system. And then now we have the sensor fusion part. Now let's talk about the control part. Again, we also implemented the simplest possible control is a PD control. And actually it's even simplified PD control. And here, and basically for the inverse pendulum, we have a damping in the control. And you can think like you have a spring. The spring has a damping. And if the damping is too low, then you pull your spring and release it, it will vibrate for a long time. But if the damping is too high, and then you pull the spring, release it, and take a long time for the spring slowly go back to the equilibrium state. And because of this, so in order for your system to go back to equilibrium at the shortest time, you want to have the proper damping term. And again, in our circuit, this damping term actually is tuned by the conductance value of a memristor. And here actually again shows the system function of this. And here, for example, you can, here we show, or this is actually shows the angle of the robot. If we hit it, then it will vibrate. And when we have a different conductance value of the memristors inside the circuit, it can vibrate. The vibration can last for a different time. And now let's talk a little bit more details here. So here, actually, we hope the robot can learn to stay in balance by itself, or finding the optimal condition for the control parameters, right? And so what we do is, again, here shows the system diagram, and we have for this analog computing part, and it's including the PD control, common filter, and the PD control, and the common filter and the PD control, and then we basically hit it. We hit it with impact. Actually, you will see later how we hit it with a consistent impact. So we hit it with impact. Then after hit it, the system will vibrate, and we'll check how fast it will go back to balance. Actually, we will use the integral of the angle of the balance, the total angle of the balance, or integral over time as the cost function. And then the system will decide, will tune the conductance value of the memristor. But before we tune it, actually, for the memristor inside the system, we also put a very small resistor in serial. And this resistor can be either put in serial with the memristor or got bypassed. And so now for every conductance value over every resistance value of the memristor, we will have two measurements. One measurement is bypass the serial resistor. The other is have the serial resistor not bypassed. So you actually effectively have two different resistance value, right? Or two different conductance value. And we will see which value make the robot more stable, which value has lower cost function. If the higher conductance one is more stable, then we will program the memristor to even higher conductance, actually increase the conductance by 100 microsiemens. And if the lower conductance one give you lower cost function, then we'll tune the memristor to lower conductance by 100 microsiemens. And then until we just keep tuning this until we don't see much change anymore, then we stop. And so this is how we tune the feedback parameters. And here actually the black dots here shows the simulation result, but the red dots are the real experimental data of how after we tune it, how everything changes. And let me actually show you, or some here actually shows some more details. And this actually shows 18 different measurements. Sorry, actually, totally we did 17 in total epochs, different tunings, but actually here we only show 12 out of those 17. But here actually you can see, for example, here you see for one memristor value, actually have two measurements. One have a conductance of 1200 microsiemens, the other have 1600 microsiemens. And it looks like the 1200 microsiemens give you more stable system. And so we continue to lower the conductance. And then still lower one give you a more stable system. So we continue to lower the conductance, etc., until in the end, we don't see much change anymore. And so here actually shows the difference. The black curve here were the first one. When we hit it with impact, how much it vibrates. And the red curve here actually shows it's much more stable. And actually here you see the line all got flat after here. And that's a real measurement data. It's just because it becomes stable, so it looks flat. And here actually, this is the zoom in view, and you can see. And first, and it's go back to balance much quicker. And second, it's vibrate much less. And this this is actually the circuit diagram. And so on the circuit diagram, okay, so first, and you see this is one memristor and this is another memristor, and this memristor can be either connect to, this is our sensor fusion part, this is a sensor fusion part, and this is the PD control part. So those two memristors can either be connect to the sensor fusion part or connect to the PD control part. And then this is the circuit we tune the memristor conductance. So this is a tuning circuit, and it's controlled by, those are essentially the analog part, but actually here we have Arduino to control it. And Arduino, of course, is digital. And then this is actually those actually coming with the self-standing car originally, including the power supply and the motor driver and other controls of the and other part of the car. For example, the display, the small display screen on the car, things like this. And yeah, those are the memristors. And of course, and we would like to compare with some other previous work. And so to put a long story short, and for this self-standing car, actually on the gyroscope, actually for this self-standing car, they actually come with a digital common filter. But this digital common filter is relatively slow, and it takes about a few millisecond time. Actually, for this one, it costs almost 9.5 milliseconds. And that's actually fairly slow. And another way you implement this is we can using a faster, we can using the processor on the car actually to do the digital common filter. And but the latency here actually will be, for the common filter itself, the calculations is very simple. The math is very simple. The most latency actually is on the communication bus. You have to send, of course, the device first imagine is analog signal. Then this ADC convert from analog to digital. Then the data had to send from the communication bus to the processor. Then processor do some calculation, and then send to the PD control. And so those actually give it about 3 millisecond latency. But of course, if you really want to make it fast, you can always put in FPGA to do it. Then, of course, it can be much faster. Then the total latency will be in the order of 100 microseconds. And but for us, actually, the digital for the analog common filter plus the PD control part, actually, our latency is about 6 microseconds. It's basically just RC delay of the system. And so it's basically the time is negligible. Actually, in the system, most latency actually is in the motor itself. And of course, I have been bragging so much about it, talk so much about it, and actually, I really want to show you a video here. Actually, shows the difference. And does it really work, right? So here, actually, what you are seeing is on the top is exactly same self-standing car. On the top, we replace the common filter and the controller with the common filter and the controller we built based on memristor. And the bottom one is the common filter and the PD controller coming with the car. So now we're using an apple, and we put apple to exactly same height and release it, and let the apple to hit it. And let's see how fast it will go back to balance. And by the way, this video is shooting at 8 times slow motion. So let's have a look. Did you see the top one go back to balance much faster to the bottom one? The bottom one shake for quite a while. Let's have a look again. You see the bottom one shakes for a while, then. And actually, I want to sorry to keep showing this, and I want to this time I want to look at the wheel. You can see if you pay attention to it, for the top car, after impact of the apple, the wheel start to spin immediately. And for the bottom one, actually, you can, if you look carefully, you can see there's a small delay before the wheel start to spin. And that's why the bottom one actually shakes so much. And so that's basically shows why the top one go back to balance so fast. That's basically the latency is much smaller. And so that's why it's much more stable. And okay, and so so basically today I talk about the two things. One is one way to engineering the characteristics of a memristor through controlled crystallinity of the switching material. And the second part, actually, I showed you the simplest cerebellum for simplest robot implemented using memristor-based analog computing and plus some digital part. And it shows much nicer performance. And again, and first, I always want to have to thank our sponsor. And this work was sponsored by Air Force Research Lab. And those two students, they are the two main key students, did the most part of the work. And of course, I also want to thank my collaborators, Professor Han Wang and Professor Joshua Yang. And of course, last not least, and thank you. And how about let me stop on this video.
Great, thank you, Wei, for a great talk. This was very interesting.
Thank you.
Again, for questions, you can write them in the Q&A feature and I can read them out loud, or you can raise your hand and directly ask your question. So we have a few questions that have already come in. So one of the questions is asking, do you have an idea why the 160-degree aluminum oxide deposition produces better material than the 200 for your application?
Yeah. Sorry, I was looking at the chat and it's different from you say. Can you repeat the question?
Oh yeah, sorry.
My hearer and my interfere each other. Sorry.
No problem. So would you know why the 160-degree aluminum oxide produces a better material for your application compared to the 200?
Oh, no. It's a 120 produced the best, not 160. It's 120. So basically, okay, depends on application. If we talk about application as a memory device, and you're switching the memory on and off using a relatively high voltage pulse, then the 120 degrees C one works the best. And at 120 degrees C, it is still amorphous. And it's the highest temperature keeping it amorphous. If you keep increasing the deposition temperature, it will be polycrystalline. And once it becomes polycrystalline, the switching will be less repeatable than the amorphous one. Actually, if you intuitively thinking, it's reasonable, right? When it's amorphous, it's the switching is more homogeneous. The material is more homogeneous. And the one is from polycrystalline, you have a lot of green boundaries. And then the filaments or conduction channel can form along the boundaries. And when it form along different green boundaries, it can be less repeatable. And so that is why. And also, I think for the curve showing, I think the question probably asked why the 160-degree one works better than 200. And the first 120 works better than 160. And for that specific one, the 161 look better than 200. Actually, that's because for that one, I think I showed you about 1,000 switching cycles for this specific device. After, I don't remember, after a few hundred cycles, the device was stuck at either on or stuck at off. I don't remember. So after stuck there, then the switching stopped. And actually, so for this experiment, we're just using pulse train, switch on, off, on, measure it, off, measure it, on, measure it, off, measure it, and record it. And if in real application, of course, you can always see, oh, if my device stuck in the on state, you can also do a forming process and try to save the device, and then the device can continue to work. And so for the curve I'm showing it here, the 161 works better than 200. That's really due to the switching protocol. If we change to a different switching protocol, it can be slightly differently. But the general trend is when we use it as a memory device, keep the layer amorphous, give you more consistent switching. And hopefully this answers your question.
Great. So just to follow up on that, are there features of your memristor device that are not optimal for the particular applications? Are there features that you would hope to have in your device?
Yes, it's a great question. And okay, so first one, the reason we pick this memristor, if you read the papers, you know there are many different material combinations to make memristors. The reason we use this memristor because this one gives us the most linear IV curve. And you can see in the circuit, doesn't matter common gain or the PD control or the parameters are all implemented by the conductance value of the memristor. And we want the memristor to be as linear as possible. So we use this one. But actually, if you look carefully, right now, the biggest thing we want to improve on this memristor is for this memristor, the resistance is relatively low. When you have relatively low resistance, which means the current will be big, and then it can consume more power. If we can make the resistance value of the memristor, let's say 100 times more resistive, then the power consumption can be not necessarily 100 times lower, but will be much lower. So this is actually one thing we are working on right now.
Great. So the next question is asking, is there a chance of ionic absorption that may impact the longer term performance of the memristor device?
Actually, that's a great point. And for this specific device, we don't know because we only measure this device up to 8,000 times. And because actually our measurement setup, actually we're using this switch matrix, and for every point actually takes a very long time to measure it. And actually it is very possible this can be one of the failure reasons for the memristor. But for this specific application I'm showing here, we are not really using this as a memory device. We're using this to tune the common gain and also the damping factor. And they don't really need to be tuned too often. And so 8,000 times is already more than enough than we ever need. So we never really studied this.
Great. So the next question is asking, as in they're curious about the 8-bit ADC and are asking if this was a bottleneck in terms of performance.
No, this is not the bottleneck. And actually, for this memristor, so we can have a 7 bits equivalent 157 different conductance value. So it's equivalent of 7 bits. Actually, not even 8 bits. Actually, 7 bits. But actually, we don't even need to have so many bits. And for a system like this, the latency actually is much more important than the accuracy. And just think about ourselves. And you really don't care about whether you are leaning to the left by 1 degree or 1.1 degree. As long as you know, oh, I'm leaning to the left and to push right. Now, actually, since we talk about this, actually, this is a fun project for us to work on. And so probably some of you read some novels about martial art or whatever. And so people say, okay, this guy is so stable for this fighter. Why this so stable? Because he did this and this exercise. And actually, I realized what the exercise means. Basically, they try to train their lower level nerves to have a response to impact. So they don't need to use their brain to think about it. So their response latency is much shorter. So that's why they stand much more stable than other people, right?
Great, thank you, Wei. We're running out of time. I just wanted to thank you very much again for the very interesting talk, and thanks to our audience for joining today. Thank you.
Oh, thank you everyone for coming, and thank you for inviting me. I mean, this is MIT, right? It's always an honor to give a seminar at MIT. So I'm really flattered.
Thank you, Wei.
Everyone.
Thanks, thank you, Wei.